Euclid's theorem. Here statement, there are infinite number of primes. Here to prove there are infinite number of primes. So proof here, suppose I will take there are finite number of primes here. So I'll take finite number of primes. I'll take here let p1 p comma p2 comma p3 so on up to p suffix n be the finite number of primes. So now I will consider f capital P equals p1 p2 p3 so on up to pn. Here this is product, not here p1 comma p2 comma p3. Don't write like this. This is product plus 1. These are all prime numbers. Product of prime numbers plus 1. So what you get here to check it here. So I consider the point. So why I taken this here? Here suppose I took two product. So 2 into 3 into plus 1. If I add plus 1 for prime number, what you get here? 3 2s are 6 plus 1 will get 7. So that means you will get another prime. So you will get another prime. So here 5 into 2. These two are prime numbers. 5 2 here plus 1. 5 2s are 10. 10 plus 1 you will get 11. So 11 is also prime number. So if I consider here this one, p product plus 1, product of prime numbers plus 1, you will get you get an prime numbers. So if you get an prime numbers, no problem. So suppose if you get composite numbers, we have to go for fundamental theorem of arithmetic. So capital P can be written as product of primes, product of prime numbers, so therefore P is divisible by some prime numbers, say Q. So Q is always greater than 1. Here by fundamental theorem of theorem, here if n is greater than 1, so here d divides n. So there exists an integer, n is greater than 1, there exists an integer d such that d divides 1, 1 is less than d and less than n. So this is your fundamental theorem here. So like that here I taken here q is greater than 1 here. So p is divisible by some another prime numbers. I take it as q. So that means here p divides q. So this implies that. So but there are only prime numbers are p1 p2 p3 so on pn. So therefore q must be q must be one of these. Q must be one of these means here, somewhere here, q divides here p1, p2, p3, so on. You'll get somewhere you'll get q, so on. You'll get p suffix n. So that means p divides some here q. So that implies that q divides p1, p2, p3, so on, pn. So and q divides p, and q divides this time is taken as p here. So q divides p minus here. What is capital Q taken? Here p1 up to pn plus 1. So take this one to left hand side. What do you get? p1, p2, p3, so on up to pn. This is product. So if you take it in left hand side, what do you get here? p minus p1, p2, p3, so on, p suffix n equals 1. So this whole thing can be written as 1, right? So this implies what do you get? Q divides 1. So which contradicts here. This implies what do you get? Q equals 1 will get. So which contradicts to q is greater than 1. Q is greater than 1, or you can write a contradiction, to q is greater than 1. So here here it is not an here q is, it is q equals 1 you'll get, but here fundamental theorem of by fundamental theorem q is greater than 1. So when q is greater than 1, if we get q is greater than 1, this becomes finite number, but here we'll get q is equal to 1. So that means you have to take it contradiction for this one. So it is finite means you'll get an infinite. Therefore these are infinite number of primes.